The story of our existence does not begin on Earth. It does not begin with the first flicker of life in the primordial seas, nor with the first hominid to walk upright on the African savanna. To ask why we are here, why this planet exists, is to ask a question whose answer is woven into the very fabric of spacetime, a narrative that stretches back 13.8 billion years to the singular moment when everything we know, and everything we are, exploded into being. Before there was matter, there was only energy, an infinitely hot, infinitely dense point containing all the potential of the cosmos. Then, the Big Bang. In less than a second, the universe inflated, cooled, and began a process of cosmic evolution that continues to this day. In those first few minutes, the simplest elements were forged: hydrogen, helium, and a trace of lithium. This was the raw material of the universe, a thin, uniform gas adrift in an expanding darkness. For hundreds of millions of years, this was all there was. Gravity, the silent architect of the cosmos, began its patient work, pulling these primordial clouds together into denser and denser knots. Within these collapsing nebulae, pressures and temperatures soared, igniting the first stars. These were not like our sun. They were colossal, violent giants, hundreds of times more massive, burning through their hydrogen fuel in a mere few million years. And in their fiery hearts, a miracle of cosmic alchemy took place. Through nuclear fusion, they crushed simple elements into heavier ones: carbon, nitrogen, oxygen. When these giants died, they did so in the most spectacular fashion imaginable, in supernova explosions that for a brief moment outshone entire galaxies. These explosions seeded the cosmos with the new, heavier elements they had created. This was the first great act of cosmic inheritance. Without the death of these first stars, the elements necessary for rocky planets, and for life itself, would never have existed. Our story narrows, some 4.6 billion years ago, to a quiet corner of the Milky Way galaxy. Here, a vast cloud of gas and dust, enriched by the remains of multiple generations of long-dead stars, began to collapse under its own gravity. This was no ordinary cloud. It contained the precise blend of elements forged in stellar furnaces and scattered by supernovae. At its center, the pressure grew immense, and a new star, our sun, was born. The remaining material flattened into a swirling protoplanetary disk. Within this disk, a chaotic ballet of creation and destruction unfolded. Dust grains stuck together, forming pebbles, then boulders, then planetesimals. These planetesimals collided and merged in a violent process of accretion. One of these growing protoplanets was the nascent Earth. In its early days, it was a hellish world, a molten ball of rock and metal, under constant bombardment from the debris of the young solar system. Then, a cataclysmic event occurred that would prove absolutely critical to our existence. A Mars-sized protoplanet, which we now call Theia, slammed into the young Earth in a glancing blow. The collision was of an unimaginable scale, vaporizing much of Theia and a significant portion of Earth's mantle, throwing a colossal ring of molten debris into orbit. This debris eventually coalesced to form our moon. The significance of this event cannot be overstated. The moon is disproportionately large for a planet of Earth's size. Its gravitational pull stabilizes Earth's axial tilt, preventing wild and catastrophic swings in climate that would have made the evolution of complex life impossible. It also created powerful tides, which may have been crucial for stirring the primordial soup in coastal pools, encouraging the mixing of chemicals that would eventually lead to life. Without the Theia impact, Earth would be a very different, and likely lifeless, world. The planet had found its partner, but it still needed the right address. Earth orbits the Sun within a region known as the circumstellar habitable zone, or the Goldilocks zone. This is the narrow band where the temperature is just right for liquid water to exist on a planet's surface. Too close to the Sun, and the water would boil away as on Venus. Too far, and it would freeze solid, as on Mars. But location alone is not enough. Earth possessed another critical feature: a planetary superpower generated by its molten iron core, a powerful magnetic field. This invisible shield, the magnetosphere, extends far out into space, deflecting the constant stream of charged particles from the sun known as the solar wind. Without this protection, the solar wind would have stripped away our atmosphere over billions of years, leaving the surface exposed to deadly cosmic radiation and turning our world into a barren desert like Mars. And then there was the water itself. Where did the oceans come from? For a long time, the leading theory was that water was delivered to the dry, young Earth by icy comets and asteroids during the late heavy bombardment. More recent evidence suggests that much of Earth's water may have been here from the beginning, locked within the very minerals that formed the planet. Regardless of its origin, the presence of vast quantities of liquid water was the non-negotiable prerequisite. It is the universal solvent, the medium in which the chemistry of life could unfold. The stage was set, a rocky planet, in the right place, with a large moon for stability, a magnetic field for protection, and oceans of liquid water. For hundreds of millions of years, this planet cooled, a crust formed, volcanoes belched gases, and a primitive atmosphere took shape. In the warm, shallow waters, a chemical symphony was underway. Lightning strikes, volcanic vents, and ultraviolet radiation from the young sun provided the energy to transform simple inorganic molecules like methane, ammonia, and water into the complex organic building blocks of life, amino acids, and nucleotides. But a collection of building blocks is not life. The true leap, the deepest mystery in all of science, is idiogenesis, the transition from non-living chemistry to a living, self-replicating organism. How did these molecules assemble into the first RNA strands, capable of storing information and catalyzing reactions? How did they become enclosed within a lipid membrane, forming the first protocell? We do not have the full answer. It may have been a 1 in a trillion statistical fluke, a process so improbable it happened only once in this galactic neighborhood. Or it may be a natural, emergent property of complex chemistry under the right conditions. Whatever the mechanism, around 4 billion years ago it happened. The last universal common ancestor, or LUCA, emerged. From this single microbial ancestor, all life on Earth, from the bacteria in our gut to the blue whale in the ocean, is descended. For the next 1 billion years, life remained simple, single-celled, and anaerobic, existing in a world without oxygen. Then came the second great transformation of our planet, an event so profound it was a global catastrophe. A new type of bacteria, cyanobacteria, evolved a revolutionary new trick: photosynthesis. They learned to harness the energy of sunlight to split water molecules, creating energy for themselves. As a waste product, they released a highly reactive, toxic gas, oxygen. For 1 billion years, this oxygen was absorbed by iron in the oceans, which rusted and settled to the seafloor, forming the banded iron formations we mine today. But eventually, the sinks were full. Oxygen began to flood the atmosphere in what is known as the Great Oxidation Event. For the anaerobic life that had dominated the planet, this was an apocalypse. Oxygen was a poison that wiped out the vast majority of life on Earth. But from this mass extinction, a new possibility arose. Some organisms evolved ways to not only tolerate oxygen but to use it in a new, incredibly efficient metabolic process: aerobic respiration. This process unlocked vastly more energy from food than was previously possible. It was the energy source that would fuel the evolution of all large, complex, and active life, including us. The planet had not just gained an atmosphere, it had gained a power source. The path to humanity was still long and fraught with peril. It was punctuated by a series of global mass extinctions, cosmic and terrestrial events that acted as great resets for the biosphere. The most severe, the Permian-Triassic extinction, wiped out over 90% of all species on Earth. Each time, life clawed its way back, diversifying into the newly emptied ecological niches. One such event, 66 million years ago, proved to be our defining moment of luck. At the time, dinosaurs had dominated the planet for over 150 million years. Mammals were small, nocturnal creatures, scurrying in the shadows. Then a 6-mile-wide asteroid struck the Yucatan Peninsula with the force of billions of atomic bombs. The impact triggered a global winter, acid rain, and the collapse of food chains. The age of dinosaurs came to an abrupt and fiery end. This catastrophe was our opportunity. With the great reptiles gone, mammals exploded in diversity and size. Among them, a group of primates took to the trees. In Africa, geological and climatic shifts caused the great forests to recede, replaced by open savanna. This environmental pressure favored primates who could walk on two legs, freeing their hands to carry food and eventually to make tools. This was the dawn of the hominids. For millions of years, numerous species of hominids coexisted. They developed stone tools, harnessed fire, and spread out of Africa. But one lineage, Homo sapiens, underwent a final, crucial transformation around 70,000 years ago, the cognitive revolution. It was not a physical change but a mental one. A mutation in our brain wiring, perhaps, allowed for the development of a new kind of language. It was not just for pointing out danger or food, but for describing things that do not exist: myths, gods, laws, nations, and money. This ability to believe in shared fictions was our ultimate superpower. It allowed us to cooperate in massive numbers, far beyond the small bands of our primate relatives. It allowed for the creation of complex cultures, the rapid transmission of knowledge across generations, and the organization of societies. We were no longer just another clever ape. We became the storytellers, the builders of civilizations, the masters of the planet. We looked up at the stars from which our atoms came and began to piece together the story of how we got here. So, what is the true reason for the existence of Earth and humanity? The narrative reveals that there is no single reason, no preordained purpose written in the stars. Instead, our existence is the result of an almost impossibly long and specific chain of contingencies. It required the death of ancient stars to forge the elements of our bodies. It required the precise location in a galactic habitable zone. It required a cataclysmic planetary collision to give us our stabilizing moon. It required a molten core to generate a protective magnetic shield. It required the arrival of water. It required a mysterious spark to ignite life from non-living chemistry. It required a planetary poisoning by oxygen to provide the fuel for complexity. It required a series of mass extinctions, including a rock from space to clear the way for our mammalian ancestors. And finally, it required a subtle shift in our minds that allowed us to create shared realities and build a global civilization. Change any one of these events at any point in the last 13.8 billion years, and the story would be different. We would not be here. The true reason, then, is not a why but a how. We are the product of cosmic chance, planetary geology, and evolutionary opportunism. We are the accumulated luck of a billion-year-old lottery. We are the universe made conscious, the inheritors of a legacy of stardust and catastrophe. The profound truth is that our existence was never guaranteed. It is an astonishing, improbable, and precious anomaly. The question that remains is not why we are here, but what we will do with this extraordinary, accidental inheritance.